Thank you very much. Thank you, Newman, for that very generous introduction. Hello, everybody. It's a pleasure to be here again. I was in a different building last time, so it's nice to see you. Very nice new building here. So what am I going to talk about today? So I'm going to talk about errors in network data, which sounds like it's going to be a really boring subject. But it turns out actually it's not. It turns out actually it's interesting. There's actually some really cool stuff here. So I'm going to talk about how we get things wrong when we measure networks. And it turns out that that not only tells you about the measurements, which is important, but kind of boring, but it also tells you about the networks. Because it turns out that the errors are not random at all. And there's a lot of interesting stuff buried in the way we measure networks that people sort of don't appreciate. They usually just measure them and say, okay, you're on a network. It turns out there's a lot more that you can understand if you look at the mistakes we make when we do it. So let's get started. We measure lots of different kinds of networks. This is pictures of the internet, food web, and stuff like that. And of course, there are errors when we measure these things. Every kind of experiment that we do in science has errors in it. But as network scientists, we often just ignore those. The typical thing you see in studies of networks is people measure some network and say it's a social network. You ask people who their friends are, and then you just believe them. In other words, we assume that the data are the network. And this is absolutely not true. The data are some reflection of the network, but there's probably all kinds of mistakes in there. If I'm thinking of a social network, like who you're friends with, people give subjective responses. What one person calls a friend, another person doesn't. There's also all kinds of recording errors and missing data and stuff like that. If you're thinking of biological networks, like protein interaction networks, there's a lot of laboratory error there. I think everybody understands there's huge rates of both false positives and false negatives in those kinds of networks. If you're thinking about ecological networks like food webs, there's a lot of error in field data. And again, there's also missing data and recording errors and so forth. Technological networks like the internet, it's well known that the sampling methods we use for measuring the internet are biased and give incorrect answers. And there's also a lot of disagreement there. I'll talk about this example. There's lots of cases where you measure the same thing in two different ways and you get different answers. You might think the internet or something like that would be a case where we'd be pretty sure what we're measuring. After all, we built the internet. But it turns out that's absolutely not the case. So all of these things contain errors of some kind, and it's important to control your errors. It actually amazes me the extent to which this is not done in network science. In every other field of science, as far as I'm aware, you have to give error bars on your measurements. You can't send a paper to a journal without error bars or p-values or something and expect to get it published. They'll just send it back and say, what is this rubbish? You need to estimate your errors. And yet, when we study networks, we often don't do that. We just analyze the raw data as if it were the network. And everybody knows there's errors in there. If it's a social network, everybody knows these things are subjective. But you basically just ignore that. There's effectively no error bars on a lot of the numbers we publish. And this is bad. So we should do that. But as I say, it's not just about doing statistics. It's also about, it turns out that the errors are actually interesting. Let me give you just one example from quite an old study now. This is, perhaps you've heard of this one. It's quite a famous study by Pony Roy-Choudhury and one of his collaborators. They studied errors in citation networks. You know what a citation network is. It's a bunch of papers and which papers cite which other papers. And it turns out there are errors there. When people cite papers, they make mistakes. So typically there'll be some typographical errors in the bibliographies of papers. You wrote out the citation of this paper and I got 2 digits the wrong way around in the page number or something like that. That happens, for sure. What they noticed, however, is, though, that there's a pattern to the errors. Namely, that you get the same typo over and over again. If the typos were just random, this would never happen. But it'll be the same 2 numbers swapped around over and over again. 10 different people will cite this paper and they all cited it wrong the exact same way. This looks suspicious, right? So there's a pattern in the errors, and well, their supposition was that this is because people are copying their citations from other people's papers. If they actually went and looked up the paper, they pretty quickly realized they had the page number wrong. But if they're just copying it from somebody else's paper, then they never do. So you can actually use this now to estimate how often people copy a citation from someone else versus actually going and getting the paper and ideally reading it. And they estimated that about 3/4 of all citations are just copied from somebody else without reading the paper at all. So so errors are important, statistically speaking, and we should absolutely do that. But also you can learn something by looking at the errors, and it turns out there's interesting stuff to learn there. So I want to start off by talking about how you estimate errors in networks. So the naive way of doing this, you think, is what we need to do is we take the measurements we made, and then you compare that to what the actual structure, the real structure of the network is, and then you can see where you got things wrong. That's how you would imagine that you would estimate errors. Trouble is, we don't know the real structure of the network. That's the whole point. That's what we're trying to measure. So it turns out that you don't need to. Turns out, remarkably, you can estimate errors in your network even though all you have is the erroneous data. You don't know what the true structure of the network is. So let's talk about how you do that. I want to start off by sort of revisiting briefly how we talk about errors just in ordinary data when you're measuring some number. You know, you're measuring some number in the lab or something like that. How do we deal with ordinary data? Because it's really exactly the same idea. So when you're dealing with ordinary data, you're trying to measure some number which is represented by this dotted line here, and what you actually have is some scatter of measurements represented by these green marks here, and the scatter comes from some distribution. That's because there's some error in your measurement. You don't measure the exact right thing. This distribution that typifies the scatter in your measurements could have all sorts of shapes, but almost universally one assumes that it's a normal distribution. It's the Gaussian distribution, standard statistics, that's what one does. So it has a mean that is centered on the true value, what we would call the ground truth value of whatever it is you're trying to measure, and it has a width that is an estimate of the size of your measurement error. That's how much the actual measurements are scattered about the true value. So you make several measurements of the thing you're trying to measure, and that's all you have. You only have the green things, you don't know the true value, and you don't know this distribution either. So the question is, can we estimate it from the erroneous data? We only have the erroneous data, can we estimate it? Of course, the answer is yes, absolutely can. The standard way of doing that is by maximum likelihood. So what you do is you write out that distribution, which in this case is a Gaussian distribution. There is just an ordinary Gaussian distribution. This is the probability distribution of your measurement. This is your Gaussian, this is just a normalization constant. Then you say, okay, let's make a very simple assumption. All my measurements are independent. They're statistically independent measurements, which means that the probability distribution of all of them is just the product of that distribution over all the n measurements that I make. So we just multiply together a big product of distributions that look like this, and I can simplify that, and it comes out to look like this. So this is what we call the likelihood of the data. It's the probability that I measured, the measurements I did, given the true value of the thing I'm trying to measure, which in this formula is represented by mu, and given the width of that distribution, which is a measurement of how much error there is in my measurements. That's given by sigma in this case. So this is the probability, and then I want to say, well, what are these unknown things, mu and sigma, these parameters I don't know? And the way I estimate that is I just maximize the likelihood. I say I want to maximize this probability. In other words, I want to work out what's the most likely values that these parameters have given the data that I saw. So it's not actually telling me the true values, it's telling me an estimate, but the most likely estimate. So just take this thing and differentiate it. Actually, technical point, almost always we differentiate the logarithm of the likelihood, not the likelihood itself. Doesn't make any difference. Log is a monotone increasing function, so the maximum of x is in the same place as the maximum of log x. Doesn't matter which one I differentiate, it'll give me the same exact answer, but almost always it's easier to differentiate the logarithm. So this thing here, the log likelihood, is just the log of that thing that I just taken. Okay, so you can do that. Here it is. Just wrote it out again. And for instance, let me just differentiate with respect to mu. So mu again is the true value of the thing I'm trying to measure, what we call ground truth. Right? So if I differentiate this expression with respect to mu and set it equal to 0 to find its maximum, I get this equation here, rearrange it, and I find that the estimate of mu is just the standard formula for the mean. It just says add up your data and divide it by the number of things you measured. Everybody knows this formula, everybody learnt it in middle school, but they don't tell you where it comes from. Right? They just expect you to take it on faith. But you don't have to take it on faith. You can actually derive this from first principles, and this is the derivation. That is where that formula comes from. That's why when you do statistics 101, they say you should not use a formula like this unless your data are Gaussian distributed. If your data have some other distribution, this formula is not the right formula. It'll be some different formula. So they always say that, of course, but everybody ignores that. Everybody just uses this formula all the time, of course, everybody does. But in principle, this comes from assuming a Gaussian distribution. You can also do the same thing for the sigma parameter, which measures the width, and you get the standard formula for the standard deviation as well. So that's how you do things for ordinary data. All I want to do is do the exact same thing for network data. The trouble is that it's a much more complicated problem. Instead of measuring just one number, I'm now measuring a whole network, which is a great big object, which I'm going to represent by an adjacency matrix A. So in other words, the thing that I'm trying to estimate now is a whole matrix, not just a single number. But it's the same principle. I'm going to write down a probability distribution that says what's the probability I got my data given the ground truth, and then flip it around by likelihood maximization. So I have some network, I represent it by its adjacency matrix, and this A, this adjacency matrix, is going to represent a true structure of the network, which I don't know. So there's some true thing I'm trying to measure, it's that matrix. And now I go and make some measurements. I make some sort of measurements that give me some data that ideally reflects something about the structure of this matrix. Those measurements need not, in principle, be actual measurements of a network. They need not be things like, are these two proteins interacting? They could be, often cases they are, that you're actually measuring a specific presence or absence of an edge in a network, but they could be all sorts of other things as well that might in principle bear on the structure of your network. Like, if it was a social network, I might measure how old people are or what gender they have or stuff like that, which definitely has a bearing on whether people will be friends or not. People tend to be friends with people the same age as them. So there are lots of other things that you could measure that might also give you a clue to the structure of the network, and in principle you can put all of those into this calculation. So actually one of the nice things about this formalism is that it gives you a principled way of taking all of the data you have and making a best estimate of what the structure of your network is, given everything I know that I measured. Some of that data might have no bearing on the structure of the network. If that's true, then nicely this method will tell you. It will say, these data don't seem to be correlated with the structure of the network at all. They're not telling you anything, not doing any harm. You just, so you don't have to sort of decide which things you should put in that will tell me about the structure of the network. You just throw everything in there, and you get your best estimate. So you measure some data, and what you write down is, so the equivalent of that Gaussian distribution we wrote down before is this thing I was going to call P of data given A and theta. So what this is the probability that you observed the data you did given the true structure of the network, represented by its adjacency matrix, and optionally some other parameters theta. So the analogy you have to think of is the data are those measurements represented by the green tick marks before. A is the ground truth structure of the network. That's sort of the mean, the middle value that you were trying to measure in the Gaussian example. And theta is some other parameters which typically parameterize the size of the error. For instance, we had the sigma parameter that measured the width of the Gaussian. So theta is playing the role, for instance, of sigma. Okay. So this is a very general sort of way of expressing that. I'll give you some specific examples in a moment. But suppose I could write down this probability that I measured the data given the true structure. Then what I do is I flip it around using Bayes' rule. I say the probability of the things I don't know, that's A and theta, given the data, is the probability of the data given A and theta, multiplied by the ratio of the priors in the standard way. Prior on the data doesn't really matter because the data is constant, so this thing never varies. Priors on these things in the top will matter, and we'll talk about those in a moment.
Quick question.
Yeah.
You're assuming that A and theta are independent.
I am assuming that A and theta are independent. In other words, I'm assuming, so theta typically depends on how I measure the network. It's part of the measurement process. It's what's introducing the error. So it's like, you know, I'm trying to measure this voltage in the lab. And the voltage has a true value, but my experimental instrument introduces some error in that. So the true value is something to do with actual physics, and the instrument is a piece of equipment I have, and I'm assuming that those two things are uncorrelated.
But in general, a joint distribution should.
Yeah, in principle, you could have a joint distribution, but in all of the cases I will consider, it's sort of rather obvious that, you know, in a social network, this is to do with, you know, subjectivity on the part of the respondents and recording error and stuff like this, and this is to do with whether people are actually friends or not, whether they interact. So this is something which in principle has a yes or no answer, and this is something to do with how I measure. So now what I want to do is do my maximization thing, maximize this probability, There are a bunch of different ways you could do that, ranging from very simple maximum likelihood things up to more complicated Bayesian methods with Monte Carlo analysis and stuff like that. I'm going to talk about one of the very simplest ones here, although there are other more advanced ones that we use when they're appropriate. So I'm going to talk about something called the EM algorithm as a way of maximizing this quantity here. So I want to know what's the maximum of this with respect to these unknown quantities A and theta, the network structure and these unknown parameters. I'm going to do the parameters first. So I'm going to just sum out A. I'm going to take this probability that I have and sum it over all values of A to get just the probability of theta given the data and then maximize that. These parameters are typically continuous, so I can do that by differentiating. Unfortunately, it turns out that if you do that, you get some hideous set of implicit equations that you can't actually solve, not even numerically. So we borrow a clever trick from the statistics toolbox. This is something called Jensen's inequality, which is simple mathematical equality. It's basically saying that the log of the average of a bunch of numbers is greater than or equal to the average of the log, which is a standard equality. It depends on the fact that logarithm is a downward curving function. It's actually a weighted average we're taking here over any probability distribution Q of I. This is just some set of probabilities that adds up to 1. So this is a well-known mathematical inequality. What I'm going to do is take this thing that I want to maximize, take its log, because as we said, maximizing log likelihood is the same as maximizing likelihood, it doesn't matter. Take its log, so that's that thing there, and then apply this inequality. It says it's greater than or equal to this thing over here, where Q of A is any probability distribution over adjacency matrices, over structured networks. Yes?
Does that imply that A is the latent variable? Because I think we can buy.
Yeah, in a way, A is the latent variable in this case. In other words, I'm going to induce a probability distribution over A. I'm not going to actually estimate the structured network. I'm going to estimate a posterior distribution over the structured network, which is the right thing to do in this case because it turns out to have quite a broad distribution in most cases. So this is true for any probability distribution Q over networks A, but it turns out that there's one very special choice of that distribution here. If you make this choice, then this inequality I just wrote down becomes an exact equality. If you just substitute that in there, you'll find that's the case. This becomes equal to that. Another way of saying that is that this choice for Q maximizes the right-hand side of this inequality, right? This always has to be less than or equal to that. So when they're equal, that's its maximum value. So this maximizes that, then they become equal, and then I just want to maximize that with respect to theta. In other words, a double maximization of this thing here, first with respect to Q, and then with respect to theta, will give me the thing that I want. On the face of it, it seems like that's made the problem worse. I took a single maximization and made it into a double maximization. But actually, it turns out that this is really useful because it sort of usefully splits it into two different operations, both of which are easy to do. Right? So the thing about doing double maximization is that it doesn't matter how you do it. The maximum is wherever the maximum is. You just get there by any means necessary and you get the right answer. Right? So I've described it as we're going to maximize with respect to Q and then we're going to maximize that with respect to theta, but you don't have to do it that way. You can do it anyhow you like and you'll always get the same answer. So the way we do it is really stupid. What we do is we just hold theta constant, maximize with respect to Q, then hold Q constant, maximize with respect to theta, and we just sort of walk up the hill like this until you get to the top. And both of those operations turn out to be easy to do. Hold maximize with respect to Q for fixed theta, we already did. That's this formula here. We said that maximizes this thing. Maximizing with respect to theta is easy, you just differentiate, which gives you this formula here. So we just do these two operations one after another and you'll walk to the maximum. That gives you the optimal values of these parameters, theta, but it turns out, inadvertently, we've also kind of got what we wanted because in the process of doing that, we also calculated this thing called Q, this probability distribution of the networks, which is equal to that from the previous transparency. But this thing in the denominator is just the probability of theta given the data. Now apply Bayes' rule to that, and you'll see that that's equal to the probability of A, the network, given the data and theta. So in other words, you do this maximization thing, it gives you the value of theta. Now you know theta, and of course you know the data because you measured them. So this tells you the probability that your network has a particular structure given the data you saw and the values of the parameters. In other words, it's the posterior distribution over network structures. So in fact, this method doesn't just tell you what the structure of the network is, it tells you exactly how likely it is that your network has every possible structure that it could. Okay. So this is a very useful thing to know. This now allows us basically to answer any question in a reliable statistical fashion that we might want to know about the structure of this network. once you know the probability distribution. So the point is, given the data that you observed, it's not certain what structure the network has, because there's errors in the data. The network could have various different structures. This will tell you exactly how likely it is to have each possible structure. Once you know that,
But in general, we don't know that we reach global maximum, but we have local maximum.
well, that is true. Yes, and so numerically speaking, there are some tricks that you have to do. You do random stuff and stuff like that, and sometimes it doesn't converge. So yes, they're definitely technical issues. So once you know this posterior probability distribution, if you want to measure any quantity that depends on the structure of the network, like degree distributions or clustering coefficients or correlation functions or path lengths or any of the things that people commonly measure on networks, call that x of a, then I can measure the expectation. I can just calculate the expectation by taking the average over possible structures of the network. So I can calculate the expected value of any quantity I want to know. I can also calculate the variance on it just by using this standard formula. So I can give you the expected value of any quantity you might want to measure on the network, and I can give you error bars on that value. So this answers sort of my first question that I had at the beginning: why don't we quote error bars on things we measure? You absolutely can quote error bars on your measures. You have to take some extra steps. You can't just use the naive data. You have to process it through this extra step. But absolutely, this is something you should do. This is just precisely equivalent to what people do with all kinds of regular data that they measure. It is absolutely extra work. Sometimes it is a lot of extra work. Sometimes the program takes hours to churn through all the Monte Carlo calculations and give you an answer. But in every other field, people are used to that. You know, if you go talk to the people who work at the CERN particle physics laboratory, they spend months doing their data analysis, right? They collect data for 6 months and then spend another 6 months just doing the data analysis, because they understand that the raw data aren't telling you everything. You have to do the data analysis. Everybody understands this, so yes, it is extra work, but nonetheless, it's absolutely an important step in the scientific process. Okay, so that's the theory behind this. Let's see some applications of how this works. So the first example I want to give you is a really simple one, so we can get the idea of how this works in practice. So the thing you have to write down in order to do these kind of calculations is that probability, the probability that you measured the data given the true structure of the network. That's the fundamental thing that you have to come up with. This probability represents your measurement process. It represents your measurement process and how it introduces errors into the data. So here's a very simple example of one such thing. I'm just going to assume the edges in my network. So I'm going to assume my data is measurement of the presence or absence of edges, and that the edges in my network are independent binary variables. They're just there or not there, and they're independent. They're Bernoulli random variables, in other words. For a Bernoulli random variable, there's two possible kinds of error. This becomes a binary classifier problem. You can have false positives and false negatives. Those are the kinds of errors. So we have two parameters, which I'm going to call alpha and beta, which are actually the true positive probability and the false positive probability. That's the probability that I observe an edge where there really is one, and the probability that I observe an edge where there really isn't one. Okay. There's also true negative and false negative probabilities, so that's just 1 minus alpha and 1 minus beta. So I don't need two parameters. Once I've got alpha and beta, I have everything. So the error structure for a Bernoulli variable is characterized by two probabilities, alpha and beta. So very different from what you're used to with a scalar variable where it's a variance, a sigma, right? For a binary variable, it's these two probabilities, false positive and true positive probability.
But of course, there are Bernoullis with different success rates.
I'm assuming at the moment that they're IIT,
gene-
but we will talk about cases where they vary.
So this is just binomial
But it's
mixture model.
GNP.
Yes, or a binary classifier in sort of machine learning language.
Well, because you put it in terms of expectation maximization. So like, for example, there's the Gaussian mixture model, and I'm assuming that my data is coming from Gaussian, or a binomial mixture model, which
Okay,
I'm
well, so
assuming
yeah,
my
so
data is
this
coming
is
from a
not
Bernoulli
even a
process.
mixture model yet, because as I said, I'm assuming that they're all IIT, these errors. So it's not even a mixture model.
Right, but I can have different coins, right? I can have
You
different
can,
riches
and I will
doing
talk about that in a moment, but at the moment, so the catch with this particular model is that if you want to use it, you need to measure your network more than once. Right? Every statistician knows that you can't estimate your errors unless you measure things more than once. If you only make one measurement, then you have no estimate of how much your measurements vary. So if you're assuming they're independent variables, you need to do the same thing with your network data as well. And this is not something that experimentalists normally do. They don't normally measure their networks more than once. They usually only measure them once. And that's a problem. So part of the problem here is that we, the people doing the data analysis, are not doing our due diligence. But part of the problem is also just that the data doesn't exist yet, because the people who are measuring it, that's not part of their culture to measure these things. But if you look hard, you can find examples where it does happen. So suppose that you measure the network some number of times, n times here. Then for each edge, I will look and see, is there a connection between these two nodes? And some of the times I'll see there is, and some of the times I'll see there isn't. And how many times I see there is or there isn't depends on whether there really is an edge there. Hopefully, if there really is an edge there, then I'll observe one more often than if there isn't one. But who knows? That's what these parameters alpha and beta tell me. So I can write down the probability, the number of times I observe an edge, I'll call that Eij, between nodes I and j, given whether there truly is an edge between I and j. That's this element of the adjacency matrix, and it turns out to take this form.
So, quick question. So,
Yeah.
do you assume that every edge is equally likely?
Yes, so the moment I'm assuming that they're IID, in other words, independent, identically distributed random variables. But in a moment, I will generalize that and allow them to have different distributions. Okay, so given that expression, I can now plug that in. That gives me my data model. I can now plug that into that general formalism I showed you before. I won't do the derivation for you, but the end answer is that I can calculate the posterior distribution over networks, and it's given by this function here, where Q sub ij is the posterior probability that there exists an edge between node I and j. Given the data I saw, what is the probability that I and j truly are connected by an edge? Okay, that's Qij. It in turn is given by this expression here, which is in terms of the data, that's Eij, but also in terms of unknown parameters, alpha, beta, and this parameter rho, which is, I briefly mentioned the priors before. Here I'm assuming the simplest possible prior, which is that every edge is equally likely a priori. I'm assuming I just know nothing about the network, so any two nodes are equally likely to be connected. That might not be true, and if it isn't, then you can incorporate additional information, but I'm going to assume here that they're just all equally likely. So this is given in terms of these unknown parameters. The unknown parameters are given by the other half of the EM algorithm, that differential equation that we worked out. That gives me these expressions here at the bottom. So I've got the parameters in terms of posterior probabilities on the edges and posterior probabilities on the edges in terms of the parameters. Now I just iterate backwards and forwards between these until they converge, which usually means choose initial values of the parameters, calculate Qij, plug them in here, get better values of the parameters, and keep on doing that until you reach convergence. So that's the EM algorithm for this case. As I say, it's a little hard to find data where this specific, very simple model applies, but here's one example that we came up with. Nathan Eagle and Sandy Pentland at MIT did a study some years back of what they called reality mining. They were interested in whether you can tell who interacts with whom by looking at proximity data. They gave a cohort of about 100 students cell phones equipped with Bluetooth software that registered every time two of them were in close proximity, meaning a few feet or something like that. And then they recorded those proximities so that on any particular day, you know whether those two people were close together. And the question is, can you infer the underlying network of who interacts with whom from just looking at those data? So this is really very a good match to what we said, effectively measuring the same network many times. So what I did here was I took data from their study from 8 consecutive Wednesdays in March and April of 2005. I took Wednesdays because, as we'll see, there is significant weekly variation in the patterns of people meeting. For instance, they meet much less on weekends than they do during the week. So I thought, well, I'll just take Wednesdays, and then that'll get rid of the weekly cycle. And I chose March and April because they're during the term time at MIT, so that was when people were most likely to meet. So now I've got effectively 8 measurements of this network. For each of these 8 days, I have whether these two people were in proximity on that day. So I have 8 complete measurements of the network. I can plug it into the formalism I had. What this is showing is for all pairs of people, so it's basically a 100 by 100 matrix, for each pair of people, the number of times they were observed together. In other words, on how many of these 8 days? Well, like on 3 of these 8 days they were observed together, on the other 5 they weren't, or something like That's what EIJ is in this case. It's the number of days on which they observe together. So that goes from 0 to 8, and almost all pairs never met. That's the big bar here. Some of them met on one day, so a very small number on 2, 3, 4, it's getting less and less. There was one pair that met on 11. The red dots are what you get if you fit the model that I just described using this EM algorithm, and then use that to predict how many times people would have met. Right? And as you can see, the red dots fit the data very nicely. But that's only true if you choose the right values of the parameters, alpha, beta, and rho. So you have to fiddle around with those so to get the red dots to go through the data, and it actually very narrowly prescribes what the values of alpha, beta, and rho are. There's a very narrow window of values which will get the fit exactly right. And this is what the EM algorithm is doing for you. That's what it does for you. When you run it, it gives you these three values of things. It's basically, it's fitting the dots to the observed data. So now I can do things like this. This shows that function I wrote down, Qij, the probability that two nodes are connected by an edge, as a function of the number of times they were observed in proximity. So it's just the function from two transparencies back, and it looks like this. It's this S-shaped thing. If they were observed many times in proximity, then there is an edge there. If they were rarely observed in proximity, there isn't. And one of the nice things about that is that it's pretty much a step function. If you observe 0 or 1 times together, then there's less than 10% chance that you are actually have a connection in the network. If you're 2 or more times together, then there's more than 90% chance. In other words, what it's telling us is the data can be really bad, but we can still make a very reliable estimate of the network, right? The probabilities that I'm getting at the edges are either very low or very high. That tells me that in every case, I'm sure that there is an edge there, or I'm sure that there is not an edge there. Even though the actual data are pretty bad. For instance, the true positive rate is only 42%. That means most of the time, even when people have a connection, they're not observed to be connected. So the data are very bad, but you nonetheless make a very reliable inference about what the structure of the network is from them.
So it can be used for link prediction.
It could be used for link prediction, although there is no sort of temporal aspect to this at the moment. But yes, absolutely, one can have missing data in these models. That's just an edge that you never measured any number of times, and then you can pick the probability of it. So that's what the network looks like. Here I plotted it with thin edges representing low probability and fat edges representing high probability. So you can see some edges, I know there's kind of this core here, and there's this little satellite group here, but there's a lot of this other stuff which is actually quite likely they're not connected. These are low probability edges around here. Now one of the things that people often ask at this point is, well, how do you know that this is given the right answer, right? Can you compare this to the ground truth and see if it's really giving the true structure of the network? And the answer is absolutely no, you cannot do that. There is no ground truth for the real world. I think it's usually machine learning people who ask me this, because I guess in their world there is ground truth often, but in my physics world there is never ground truth. You know, if you're measuring the speed of light or something, the best you can do is, you know, make your experiment as accurate as you can. You can't go ask God, what is the ground truth value of the speed of light? There's no ground truth for the speed of light. You just measure it as accurately as you can. So, no, you can't really do that in this case, but there are things that you can do to see if you're getting sensible answers. So I told you that I used Wednesdays. I could do the same calculation for Thursdays and see if I get the same network. And the answer is no, I don't, but it's similar. I deliberately put all the nodes in the same places on these two plots, and what you see is the network looks sort of similar, but there are some differences. And that's exactly what you expect, because there's errors in the data. That's what errors mean. You measure the same thing twice, you don't get the same answer twice. But they look sort of similar, which provides some hope. There was a question back there. Yes?
It's related, exactly related to that one. Because the question, you know, of how you interpret now the network that you get. Because from what I understand, now in comparison to how machine learning is doing. So from what I understand, you make now this model assumption, right? If you,
Right.
you know, you make the assumption, okay, you really have this binomial distribution, and you have a probability that, let's say there is something like an edge, and have a probability that they may really interact, and have a probability that they don't interact even though there is an edge, right?
Right.
But this is kind of your assumption that this is the true network, right? And what you said now with your analysis is there's only a very narrow range of parameters that support your model assumption.
Right.
Namely that this is the network. But this is exactly then the question. I think, you know, then related, or let's say the opposite question, related to the answer whether the hexagon truth is, what is your network? What do you think it doesn't correspond to? Is it
Oh, I
something
see.
like a
Yes.
friendship, or
Absolutely.
what is
So
it?
that is an excellent question, and this formalism cannot answer that question. So what this formalism is telling you about is you're saying you're assuming there is some network that drives people's propensity to be observed in proximity to each other.
Yeah.
And whatever that network is, this is inferring its structure. But it doesn't tell you whether that's a friendship network or it's who's going to classes with whom, or there's many things that it could be. And this says nothing about the sociology of the problem. It only tells you there is some network that is driving the data, and you're inferring that.
And from the machine learning perspective, now the problem is, this is just because we only have 8 observations of the data, or the network is, the problem is now the data is not good enough to tell you necessarily if you can compare with a different modeling approach. Because you could say, okay, now let's assume, I have now, let's say, I have different propensities for everyone, so I drop the identical distributed assumption, for instance, and would this now explain my data better, for instance, or would there be another network that still could explain this, but under different assumption how people get active, or edges get activated.
Right, absolutely. So two things one can do to address those questions. One is one can do things like this, and I'll show you various sort of attempts to compare to ground truth, although, as I say, none of them are perfect, so you can do that. The other thing you can do is model selection of some kind, and I'll talk about that as well, mostly in a Bayesian context. The third thing I'll say is, of course, absolutely, the model is really important. I've made assumptions about the model here. One does this in all of statistics. Every time one does statistics of any kind, even if you're just calculating a mean, you are making an assumption about a model that relates the true ground truth to the data you observe. So this is always true in all of statistics, but absolutely, this is something that one needs to know. It's asking questions about what is your measuring process and how does it introduce errors, and that is something that you have to think about. And I think, in a way, an advantage of this is it encourages people to think about the measurement process and how it's introducing errors. But absolutely, that insight has to go into how you construct the model. There was another question.
I think in relative mining data, there's also a time of interaction that you can measure. So what will happen instead of just binary variable, Wednesday these two people come to close proximity, instead of saying they work together for 10 minutes in the morning or 20 minutes in the afternoon, then you might have a better measurement.
Right, so absolutely. So you could have more data. Actually, so let me talk about that. So I don't really think this is the right thing to do. Really, the right thing is if you have data for Wednesdays and Thursdays, you should put all of that into your calculation and get a better inference of the true structure of your network. Right? You shouldn't really split it up into two halves and do them separately. In fact, since I have data for all days of the week, let's just do that, put them all together, and I get better inference of the structure of my network. This is a more complicated model now. I'm assuming different values of alpha and beta, different true and false positive rates for the different days of the week, because in principle we can have them. And now, one of the things that tells you have better inference is that the probabilities have become polarized. Most of the probabilities are now very close to 0 and 1. In other words, you're very certain about the values of your edges. Here's the distribution of edge probabilities. It's just a kernel density estimate. And you'll see that the probability density is concentrated about 0 and 1. One way to quantify that is to calculate how much entropy you have per edge in your network, which is a measure of uncertainty. And in this case, it's extremely low. So its maximum value could be log 2, about 1.69, and it's actually 0.04. So this is telling you have very little uncertainty now about the structure of the network by combining all of the data I have on different days. But now, take a look at the parameters. Turns out the parameters are interesting as well. So I told you that looking at the patterns in the errors can be interesting. Here's a very simple example of this. This is the alpha and beta values reparameterized a little bit in something called recall and precision. Recall is how often you observe an edge that is there. And precision is how many of the edges you observe to be there are really true. Right? So one's like probability of A given B, and one's probability of B given A. And what you see is that precision is high across the board, meaning your data are basically very reliable. If you see an observation, it's a very reliable indication that people are interacting, but your recall is terrible, especially at the weekends, meaning there are lots of people who interact that you don't observe them interacting. And of course that's true. We're talking about people talking to their friends. You have lots of friends that you don't see every day. Absolutely. Everybody knows this, right? So we expect these numbers to be low, and yet what this is telling us is we can get very reliable inference of the network structure, very low entropy, despite the fact that the data are really pretty bad in this sense. Yeah?
Yeah, sorry, Explorer, do you have any measure of the robustness of predictions, such as feature information, how easy
You mean robustness with respect to changing the model? In the network or on the parameters? No, I don't for this case, because I'm using this EM algorithm which gives you point estimates. But I will talk about some Bayesian methods in a moment which do give you things like that. Yeah. Okay, so now in the remainder of the time, just the last few minutes, let me just quickly run through some other examples of things we've done. Here's another social network example. There's this thing called AdHealth study, the US National Institute Study of Adolescent Health. It's a big study of friendship networks in schools. So this is a much more conventional kind of social network. They didn't measure the network more than once. They only measured it once. What can we do in that case? Well, it turns out you can still do error estimation because they sort of effectively measured things more than once because they ask everybody who their friends are. And so person A will say they're friends with person B, and maybe person B won't say they're friends with person A. Right? So you measure each edge twice from the point of view of the two people involved, and that, it turns out, is enough to do this same thing again. So it's a more complicated model, and in this case, to address the question asked earlier, I'm also allowed to have different probabilities for different edges. In particular, I have a different true, false, positive rate for each person, because I assume that some people are more reliable reporters of their connections than others. Now, I'm fitting a larger model, the equations become more complicated, but you can still do this. And you can, again, infer networks where the thick edges are likely to be a connection here, thin edges are not likely to be a connection here, but also the colors here represent how truthful people are being. I can now estimate who's an accurate reporter of their own social network. So bright colors are more accurate people and dark colors are less accurate people. So again, it turns out that there are patterns in these errors. You can learn something about the system by looking not at the network, but at the errors on the network. Here's an example with my colleague Elizabeth Brooke at the University of Michigan and Marcus Schaefer. We've been studying a retirement community. There's a lot of interest in studying the elderly these days. So the retired population is becoming ever larger. We were doing a social network study of a retirement community. There's some good and bad things about that. Retired people in retirement communities, they tend to be very bored, and so they're really enthusiastic about participating in surveys. They're like, yes, that's great. They're very enthusiastic, they fill out every question, that's great. The downside is that they sometimes can't remember the answers. Because, these are elderly people, some of them have Alzheimer's, some of them have age rating, cognitive decline, some of them just have poor memories. So, we calculated this precision score that represents how accurately they can recall their own interactions. And what this plot here is showing is their self-reports of how good their memory is. Like, oh yeah, I have a terrible memory, or yes, I have excellent memory. Versus the precision scores that we inferred by looking at the data. So this is kind of another way of checking against ground truth. But here it's ground truth for the parameters, not for the network. The parameters are telling you how accurately people are recalling their friendships, and we have an independent measurement of how accurately they recall them because they report that. And it turns out that there's a strong correlation between the two. In other words, I could just look at the network and I could pick out who are the people who are having memory problems without them ever reporting that. Just because I can infer that they have worse accuracy in reporting the interactions. Here's an ecological network example. This is a food web, a paleo food web from the distant past, assembled by Jennifer Dunn and her collaborators at Santa Fe Institute. They were interested in reconstructing ecological networks of long extinct species. They do this by looking at a variety of fossil data, like gut contents. I see a fossilized species and it's got another one in its fossilized stomach. Just ate it. Or damage patterns. I see tooth marks on this fossilized species. So they assembled various different kinds of data for deciding who eats who in the long dead species world. So we can make a model of that in which we now have various different kinds of data. So I have a number of measurements of an observation between connection between nodes I and J in various different modes, gut content, body damage, all of those kinds of things. So it's again a more complicated algorithm. I have different true and false positive rates for every kind of measurement, but I can write out the equations, I can do the calculation, get the probabilities of the edges. Here's another example of how we can compare this against a sort of ground truth. They, Jennifer and their collaborators, they're experts on this stuff. They've been working on this forever and they know what they're talking about. So based on the data they saw, they made expert judgments about where the actual interactions were in the network, which species were eating which other species. I did something much more basic. I just took my predicted probabilities of edges. So in their judgments, they divided everything into low, medium, and high probability that there is a connection. So I just divided my probabilities. If it was greater than 90%, I said that that was high. If it was less than 10%, I said that was low, and everything in between is medium. Right? So very simple, dumb thing. Turns out if you do that, it gets 84% of edges are predicted, that they predicted are predicted correctly by this algorithm. In other words, most of what the experts get, you can get just by fitting their data to the appropriate variable. There are some interesting things though, again, when you look at the parameter values, there are interesting things in the pattern of errors. Here are the true and false positive rates for the various different kinds of data they considered. It's telling you some of them are good and some of them bad. So this is new useful information that was hidden in the data that they didn't have before. It's telling you now which kinds of data are good for this particular kind of network. An interesting one is this one here, gut contents. I saw a fossilized specimen of this species inside the gut of this other species. That's the one that they use as their gold standard. They consider that. If you see that, there's definitely predation going on. Turns out actually that's one of the least reliable modes. Right? The true positive rate is quite low, the false positive rate is quite high in this particular case. So actually, it's telling you that's not a reliable mode at all in this particular data set. So there's a new information here, which is perhaps surprising.
How do you reconcile that if you find the animal in the stomach and have not eaten?
Well, so there are things that can happen, like you sort of get overlays, like this fossil was laid down first, and then 1,000 years later, this other fossil was laid down, but those end up a millimeter apart in the structure of the rock, and it's hard to tell that there was 1,000 years between them. So,
Exactly, so location of the time.
yeah, it just happened to be like on top of the other species at the time. So there are ways that this could happen. So, let's see. I'm sort of running out of time here. So, another ecological network. We looked at a plant pollinator network. This one is perhaps interesting because we used a much more complicated model for this one. It turned out, so this is an ecological network of plants and insects that pollinate them. So we had to use a more sophisticated Bayesian approach to do the inference. Here, there's many different sources of error, but a primary source of error in this particular network comes from just variation in the abundances of species. Some species are more abundant than others. Some plants are really common, some plants are not very common. And the ones that are common you observe more often than the ones that are not common. Unfortunately, the experimenters don't measure the abundances. So that's effectively a source of error in your data. One of the interesting things is, one of the parameters that we put in our model is the abundance of the plants, and another one is the abundance of the species, and we're inferring those values. So we can actually work out what the abundances are by looking at the data, precisely because abundant species will be seen interacting more often, and we're fitting that interaction. So it turns out that, if you talk to the ecologists, they'll complain, oh, we don't measure abundances because they're far too hard to measure. Turns out the abundances are actually already there in your data. You just have to extract them in the right way. So again, the pattern of errors is telling you something interesting. I'm going to skip ahead here to one final example, some work I've been doing with Stephanie Forrest's group on the structure of the internet. The internet, as I mentioned at the very beginning, you'd think we'd know the structure of that network, but actually we don't. There's all sorts of sources of error. So we're looking at data that comes from BGP, so that's the protocols that routers use to route data around the internet. So the way people do this is you go and make friends with somebody who runs an internet router, and they give you a copy of the routing information bases, the databases on the router, which tell it the routes that it's using to every other point in the network. That gives you effectively a tree. Basically, it's a tree of shortest paths from one starting point to everywhere else. This tells you something about the structure of the network, but definitely not everything. So what it does is it tells you, well, obviously it tells you the presence of some edges. If you see a connection in this tree, then there's probably an edge there. But it also subtly tells you some other stuff as well. For instance, it tells you that this edge here is not present. Because if it were, there would be a shorter path, 2 steps to that node, than the one I observed, which has 3 steps. So it tells you some edges are present, it tells you some edges are not present, and then some edges it doesn't tell you anything. This one here might be there, might be not. You can't tell from looking at this data. So you precisely get yeses and nos and missing data. And then typically what you do is you take trees that are measured from many different starting points in the network and you put them together. The naive thing is people just do the union of trees, and every edge that you observe at least once is called a connection. But we can do much better than that. Now we have repeated measurements, we have yeses, nos, and don't knows. You put all of those into our model, and you can infer structures of the network that way. In this picture, again, thickness of edges represents how certain we are that edges exist. So this is actually for the internet in France, who chose relatively small portions so we can make pictures. This is the United States, bigger and therefore less easy to see what's going on here. But in
What do
principle,
the node colors mean?
the node colors, the yellow ones are nodes that are in the United States, and the blue ones are nodes that are connected to us in the United States, but are themselves not in the United States. Yes, question?
Can you also represent something like, you're very certain that some edges don't exist? Because he's showing you the certainty of the edges, like you're also certainty about the edges are not there, right?
Yeah, well, I wouldn't say certainty. Yes, so you have some non-measurements, but the thing is, you then do this many times, in principle, from many different starting locations, and you get measurements that don't agree. Right, so that's perhaps the surprising thing about internet data, is that we're actually not certain about the structure of it. You have measurements, you have non-measurements, and you have don't knows, and you do this many times, and you get things that don't agree with each other. This is certainly actually a simplification of what's going on, quite a long way, but that's basically the idea. So that's the end of what I had to say. I want to stop talking. I'm happy to take questions in a moment. Let me just summarize by saying, first of all, that people should be measuring their errors. This is an important thing that everybody else does in every other field. Why are we not doing it? The catch is it requires work both from us as the people analyzing the data and at the experimental stage, and that's not necessarily being done. And as we've discussed here today, there are important questions about how you specify the model that captures the structure of your errors, and that is crucial in doing. That's crucial in all of statistics, but it's crucial here as well, and there needs to be work done on that. Once you do that, however, it turns out that there's lots of interesting stuff to be learned about your data from looking at the patterns in the errors. You're not just making better estimates of networks, you're also learning new things about the systems you're studying because of the way the errors look. I just want to say thank you to my terrific collaborators. Elizabeth Cook and Marcus Schaefer worked on the social network stuff. John Gabriel Young and Fernando Valvinas worked on the ecological networks, and Stephanie Forrest-Bennett was a Chris Labour working on the internet stuff. I have a couple of papers out about this, which you can see here. These people gave us money. Thanks to them. Thanks to you for your attention. And that's it.
So, thanks for this wonderful talk. It's so amazing to hear. I have 2 questions. Like, you can estimate alpha, beta, like true positive, positive. Can you also infer false negative rate as a parameter? Because that will help me answering the question of my reviewers when I write a grant that you construct a network from minimum sample, how many lead samples, how good your power is.
The false negative rate is just 1 minus the true positive rate.
Sure, but like how many samples are enough to get the good network? How do I answer that in my grant?
Oh, I see. Well, that absolutely depends on the nature of the samples and how much variance there is. So what this will give you is a posterior distribution over network structures. So it'll tell you the posterior probability that the network has any particular structure. And if that distribution is narrowly peaked, meaning that most edges have either very high probability or very low probability, you have that thing where the probability distribution is at 0 and 1 and there's very little in the middle, low entropy, then it's telling you that you've got a very good estimate of your network. If the entropy is higher, then either you need to take more data or you need better measurements or something like that. So yeah, it's the structure of that posterior probability that you need to look at and whether it's narrowly peaked about a particular answer.
I was just wondering if you could characterize a little bit how these results would differ from doing it like the dumb way. So the dumb way is I got multiple measures on my network. For each edge, I've got a few measures. Say I've got 8 measures in your version. For each edge, I've got 3 1s and 5 zeros or whatever. Then I can infer a p or an alpha and a beta or whatever I want on that edge. It'll give me a distribution on the edge, and that will give me, some mean for, the overall p of the edges. Or if I want to know the distribution over network parameters or network statistics, I can just, bootstrap across a bunch of these sort of samples, assuming all the edges are sampled.
Well, so it depends what you mean by doing it the dumb way. So, suppose I want to calculate something like path lengths between pairs of nodes. Then I need an actual structure for the network in order to do my breadth first search or something like that. So in order to do that, I really need some posterior distribution over network structures so that I can average path length over that distribution. So I can infer some posterior distribution by putting some model on individual edges. I could say, let's forget about it being a network, just look at an edge as a binary classifier type thing, and I measure it some number of times, I get this number of positives, and I fit a model there. And that is essentially what we are doing in the very simplest version of this calculation, because there the edge is assumed to be independent. However, in all of the other ones, I didn't talk about this, we're also assuming that there's correlation between the network edges. So the fact that it's a network now matters. You're not just doing it at the single edge level. And the very simplest way you can do that is to use a more sophisticated prior on your network structure. So very often we use the so-called configuration model as our prior, rather than independent edges, which is equivalent to an Eddy-Shreni random graph, which is not a very good model for those networks. So as soon as you move away from an independent edge model, like the Eddy-Shreni model, then you have correlations between your edges. And then, in effect, you're using information from other edges to estimate the probability of this edge, and in principle, that gives you the ability to do better than you can do with a single edge model. There are other ways you can introduce correlations as well. That's the simplest way.
So I'm wondering about the difference between actual measurement error and starting with a bad model to interpret the data. So in the case of the MIT study, there could be measurement error of the devices don't function very well when 2 students are near each other. There would be true measurement error. And there's also the fact that the model, or whether there is an edge or not, with a certain probability, is not a good model because it's going to be a frequency at which there are people that are good friends that meet every day, and there are people that are still friends but meet once a week. So if I think about very good equivalent of biological networks, if I put a bunch of proteins, they have a binding probability, and if I was to do this study to say, well, they either bind or not bind, and it's an error, that would not be a very good model. I would need to know at what frequency they bind. And so if I do enough measurements, I imagine that even if there's no measurement error, I will still be left with a probabilistic answer. While if I have a good model, I should converge to, effectively my standard deviation should go to 0.
I think this may be mostly a semantic issue. So what I'm calling an error is actually the same thing you're talking about. So the primary source of error, for instance, in that reality mining study, the MIT study, is just that people don't meet their friends every day. So it's not measurement error in the sense of my cell phone malfunctioned or stuff like that. It's not like laboratory measurement error. When I say a false positive or a false negative is just these 2 people really are friends, but they just didn't happen to meet this day. So the effect you're talking about is absolutely already included in the model, and in fact that is the primary effect that is introducing error into this measurement. So maybe error is not the right word for it, but the measurements are not the network. The measurements are merely a reflection of the network, and that's the thing that the model is.
But I think there is a difference because if you have a statistical process and you make enough measurements, your standard deviation will go down and you will converge to a true,
absolutely.
to
if you could extend this
answer.
Study for several years instead of just 8 weeks.
I think so. Fine. So that's after that. That's a technical problem of whether I want to extend it, whether it makes sense to extend it, depending on what model I have, right? So, but I think sort of what you could learn from this, it seems to me, is when your model is not complete. So, in the sense of looking at the convergence, because if you don't have a good model, as you take more and more data, you go for years, you would still end up with probabilistic answer, and you would not be converging.
Yeah, absolutely.
So is there a rate of convergence or something?
Right. If you think about this picture that I drew for that particular study, This one here, in this case, the model fitted pretty well.
Yeah.
But it could be that even the best fit to the model is not a good fit.
Yeah.
Which in this case you could do by doing a chi-square test or something on this histogram, right? So you can do some post hoc test that will say, even your best fit to the model is still not a good fit, in which case you need to change your model.
I think that's interesting.
That is a standard part of doing statistics, of course. There are cases where your data are clearly non-Gaussian, and now you shouldn't be using a Gaussian model. You could do a similar sort of
Or you shouldn't be using the fact that there's an edge or not an edge. There's actually a weighted edge.
This is the equivalent. Yeah, right, exactly.
Let's take one more question.
A lot of the thinking seems to be going on at the level of the data model and prior. Also, can you give some sort of a comment on the choice of the data model, and how you would know if you're making a right decision?
Yeah, well, so the bottom line here is that you need to understand your measurement process. And so you need some domain expertise in the particular area you're working in, and I admit that in many of these cases I don't really have that, which is in part why I'm working with other people who do the actual measurements. It's great to be talking to people who do the measurements. However, there are also technical things that you can do to make the situation better. One is, as I've talked about, you can do post hoc tests to see whether your model actually fits the data well. Another is you can do.
Use, let's say, the simple model for the mutualistic case or for the ecological case. How would you have known that you made a mistake?
So you might do something like this, where you resample the data from your model, and you find that even your best fit doesn't represent the data at all well. The data that the model predicts you would get don't look anything like the real data. That's what you would be saying if the red dots here didn't go through the histogram. So you do post hoc tests to see whether even your best fit is still a poor fit, in which case your model is bad. Another thing you can do is model selection. If you have a family of possible models, ideally quite a large family to give you lots of flexibility, then you can ask, from this family, which is the model that best represents the error in my data? And there's a well-established bunch of statistics which gives you techniques for doing that sort of thing, starting with simple things like the Bayesian information criterion, but also more complicated Monte Carlo model selection techniques and so forth. So in principle, one could do all of those things with these kind of data, although it's early days yet, and we haven't.
Okay, we're already over time, and let's thank Mark.